Ready, sir?
Yeah. So you start with this one. This is a very basic question.
Okay.
Satish Kumar,
Huh.
the last one.
And then reverse.
Yeah. Then reverse this one. Yeah.
This is you can start.
Hmm?
You can
Yeah.
start.
Yeah.
Hello, welcome to the live session for this course, an introduction to smooth manifolds. We have some questions here which were asked earlier, and I think we can start right away.
Yeah.
So I'll ask the first question. It's from Satish Kumar T from IGCAR Kalpakam. They ask, I understand that the differential, the push forward, is a linear map between tangent spaces and is represented by the Jacobian matrix. What I could not comprehend is how Jacobian matrix multiplies with an x of one tangent space to give a y of the other tangent space. Can you please show how it should be written?
Okay. So since this is a very basic question, let's start with this one. Okay. Now. So in short, the question being asked is, how does the Jacobian matrix, well, I'm paraphrasing the question, but it amounts to saying, how does the Jacobian matrix represent the differential of a smooth map? So let me again quickly go over the two sort of seemingly independent notions of the differential of a smooth map. So two notions of a derivative or differential of a smooth map. When we started the course, we just dealt with open subsets of Euclidean space, and so this is the first notion. The first one is, so let F from, for simplicity I'll just take, instead of dealing with the domain being an open set, I'll just take the whole of Euclidean space Rn to Rm be a differentiable map. Well, i.e. for any P in Rn, there is a linear map. This is the way we define differentiability of a map between Euclidean spaces. There is a linear map which we called capital DF or small df when I started the course.
For manifold small d.
Okay, in that case, for Euclidean space, it was capital DF at P. There's a linear map, and again, this map is again between Rn and Rm. Such that the defining property of this linear map is that limit h going to 0, norm of f of p plus h minus f of p minus df at p acting on h divided by norm h is equal to 0. Well, now this, it turns out we saw that this defining property actually forces the uniqueness of this map. In other words, such a linear map may not exist, but if it does exist, it is unique. We saw all this in the beginning of the course. Now notice that DFP by definition is a map from Rn to Rm. And a concrete way, since it's a linear map, we know that every linear map between Rn and Rm can be represented as by a matrix. In other words, we know that there is a so the number of Rn to Rm. So what is the size?
Rn to M. It's
M cross N.
yeah, M cross N.
M cross N. There
Yeah,
is
M cross
a M cross N matrix. Let's call it JF at P, such that DFP acting on V is the same as the usual matrix multiplication of JFP with V, where V is an Rn and we think of V as usual as a column vector. And further computation, small computation, will show us that in fact this JFP is the familiar Jacobian matrix. The IJF entry of this matrix is, it's nothing but del Fi by del Xj. So here I runs from 1 to M, J runs from 1 to N. So this F is F of X equals F1X Fmx. So this is the Euclidean side of the story, and this is quite this part of this what one encounters in multivariable calculus. Now the the other definition of derivative that we saw was in the context of manifolds. Here I have a smooth map between a manifold of dimension n and a manifold from a manifold of dimension n to one of dimension m. And in this case, so let's say let f from here to here be smooth. Again, we want to define the derivative at a point P. Let P in M Now, the first thing is that in the Euclidean case, the derivative was a linear map between the same two same two Euclidean spaces, Rn and Rm. Here, however, the derivative, which I now denote with a small d, DFP will be a linear map between the tangent space TPM to the tangent space at TF of Tn. Then DFP is the linear map defined by. Before I proceed, the key point here is of course the definition of DFP depends on what constitutes a tangent vector. We saw that this itself is a somewhat defined in a somewhat strange way in the context of manifolds. namely a tangent vector at the point P to the manifold M is by definition a derivation on the space of C infinity functions on M. The derivation is based at P. So it will take a derivation here to a derivation here. So let's take a derivation V. So I start with a V in TPM, which is a derivation on C infinity function. This is supposed to give me a derivation on N. So in other words, I have to specify what it does to the function on N. So let's see. So this I define to be V of. So this picture, in terms of picture, so I have this is F. This is this
You
is.
can use another.
Oh, sorry, yeah, right. F has already been used here. I wanted to say P. So this is P and R. P composed with F will be a C infinity function on M, and I let the derivation V act on that. So this is the very definition of a derivative for manifolds. But in either case, by definition, the derivative will be a linear map between corresponding some vector spaces. Of course, we also saw that how these two notions are actually, they agree with each other when the underlying manifold. In the second case, if I take M to be Rn and N to be Rm, and the key point is, in that case, I can identify TPM with Rn, and this with Rn. If we use that identification, so if M equals Rn, N equals Rm, then I have this identification with Rn and Tf of Pn. And this identification is not something it's not the fact that TPM is an n-dimensional vector space will say that this is isomorphic to this in general, but the point here is when the underlying manifold itself is Rn, then there's a natural identification, natural in some sense, which we saw. And if we use this, so the identification, instead of using the isomorphic sign, let me just write as a map. So TPM, so here let me call it Pn, P capital Pm, and then I have this, well, this was my small dfp, and the point here is that when I look at Rn as a manifold, then I get the second picture of the derivative. If I forget the manifold structure of Rn and just go back to my first definition, multivariable calculus definition, I can still talk about the derivative. That will be my capital DFP. What I want to say is that this, if I identify TPM with Pn, with Rn via this map Pn, and likewise on the right side, then these two maps are the same. In other words, we then have, I can go like this, df of p, and I can do pm, or I can do this, dfp pm. I can even since this capital Pn and Pm are isomorphisms, they have inverses, so I can write this equation as Pm composed with dfp Pn inverse equal to df. So this is not as complicated as it looks. All it's saying is that two notions of derivative, in case the underlying manifold is Rn, they're the same if you ignore this Pm and Pn. If Pm and Pn were literally identity, of course I would get these to be the same. Otherwise, you have to throw these isomorphisms, which are natural, and then they will be the same. And so we did this, and I repeat that the key point for proving this last equation that I had was the fact that the tangent space to Rn or Rm can be identified with Rn or Rm via this capital Pn, natural map. In fact, this identification was the starting point for defining tangent space to a manifold, for showing that the tangent space is finite dimensional, of dimension n, and so on. Everything hinged on this description of the tangent space. So hopefully that answers the question. Now let us move on to the second one. Yeah, so first let us see, get back the, yes.
So the second question is also by the same person, Satish Kumar T. And the question is, I could not understand how the constant rank theorem is a consequence or corollary of the inverse function theorem. Can you elaborate, please?
Alright. So this one requires a bit more work. It's not just a conceptual issue. One actually has to do some work. And for details, I'll refer Satish Kumar and whoever else has the same question to Lee's book, which has a nice exposition. It's okay, I can know this. So this, how does the constant, what is the inverse function theorem? But let's just look at a simple example. Inverse function theorem imply the constant rank theorem. So let's recall the constant rank theorem first. So this states the following. Suppose I have f from an open subset of Rn to Rn. Suppose f has rank k at, oh sorry, not f, df p as rank k for all p in U. So this is my U, this is f, this is Rm. Right. Whatever point I take in the domain, the derivative should have the same rank. Now, before I begin, I should mention that I'm talking about the constant rank theorem in the context of open sets in Rn. Once we have this, it's an easy matter to generalize this to manifolds, but the Euclidean space constant rank theorem is the main thing. So let me just explain this. Right. So suppose a DFP has rank k for all. It's suppose I should say that there exists k, a positive integer, such that the k should come before I make a reference to the point. Suppose there exists k such that DFP has rank k for all p in U. Then for any p in U, there exists a neighborhood V contained in U and containing P. So this is my V. Neighborhood of this P and a neighborhood W of, so this is f of P is somewhere here, so I want to put that inside a small neighborhood W as well. Neighborhood W of f of P and what else? Well, then change of coordinates, in other words diffeomorphisms, P and C here to, let's say, what I've been calling in the course V1 and W1. These are again in Rm, this is in Rm. All the stuff, this, and diffeomorphisms. P from V to V1, C from W to W1, such that the point is that so one should think of this diffeomorphisms as changing coordinates. After I change coordinates in the domain and image, the map looks like a projection. That's what I want to say. So after changing coordinates, I want to saying that first I go by P inverse, then I look at the map F, then I use the new coordinates on the target C, acting on x1, x2, xn equal to x1, xk, now notice that the maximum possible value of k, the rank of df, is basically the target dimension m. So k is always less than or equal to m, but k can be equal to m. That's the case of a submersion. If k is equal to m, there are no zeros here. Zeros will appear if k is strictly less than m. So let's look at one very simple case. So let's look at example. Let's start with a map from, let's say, R2 to R2. Yeah, U open subset of R2 back to R2. And let's say that, let's assume that DFP has rank, oops, I sort of use my new notation, the manifold notation for derivative, but
take that up later.
So let me finish this. Yeah. So this derivative, anyway, we saw that the two derivatives are the same. So think of, if you don't want to think of the derivations and such things, just think of this derivative as a Jacobian. That's good enough. This DFP I'm using interchangeably with the multivariable calculus derivative. So DFP has, let's say, has rank 1 at every P. So constant rank theorem, in this case, there are only 3 possibilities for the rank. The rank can be 2 at every point, rank can be 1 at every point, or the rank can be 0. So before I start the rank 1 case, let's dismiss the easy cases first. If DFP has rank 2 at every point, then so then we are back in the realm of the inverse function theorem. So in other words, the derivative will be invertible. Then the inverse function theorem applies at every P in U. So the inverse function theorem tells me that it will give me a neighborhood like here. So back to this picture, if I apply the inverse function theorem, I'll get a neighborhood V and a neighborhood of W of f of P, such that f is actually a diffeomorphism from V to W. But what about this P and C in that case? Well, so here what happens is at every P. So we get neighborhoods V of P, W of f of P, such that f takes V to W, and this is in fact a diffeomorphism. This is a diffeomorphism. So now now it's quite clear what to, if I want to formulate it in these terms, if I want to find this P and C, it's quite clear what to do. Well, all I do is, for instance, I can take, so this one, the first one I called P, I just take to be F inverse, and this I take to be identity W, so this will be again W. So this is my C. So the map C composed with F composed with P inverse. Oh, not P inverse here, it is F itself, not F inverse, F itself. Identity composed with F composed with F inverse equal to identity. So obviously, trivial, in a very trivial way, x1, x2 will be equal to x1, x2. So when the rank is 2, I do these diffeomorphisms P and C are not really that interesting. They don't even make an appearance. It's just F itself. I can use that. Now, and the other trivial case is the rank is 0 at every point. We know what that means. If rank DFP equal to 0 for all P in U, then that means that the derivative itself is 0. So f is a constant now.
This was also an assignment question.
Yeah, this was an assignment question. But in fact, if we want to state it exactly like what I did here, if I want this form, I still have to choose some phi and c. I mean, after all, f is a constant, let's say q, i.e. f of x equals q for all x in u. But according to this equation, that the green equation that I wrote here, if f is a constant, I should get k is 0. So in other words, the x variables do not appear at all. Only 0 should appear. So what I would like to get is, what I want is some diffeomorphisms C composed with F composed with P inverse of x1, x2 should be 0, 0. But what I have is f of x1, x2 is equal to q1, q2 for some fixed q1, q2. Now it's quite easy to see why you can make it 0, 0. Just take let phi, the diffeomorphism phi, to be the identity and C to be a translation. C of x1, C of x equal to x minus q. Then you are done. Then C composed with F composed with P inverse of x1, x2 will be 0, 0. So these are the easy cases, but the more interesting case is the rank 1 case. So let's see what inverse function theorem has to tell. So here rank equal to 1. Rank of the DFP equal to 1 for all. So actually what one uses is not quite the inverse function theorem, but a closely related theorem, the implicit function theorem. So the hypothesis for implicit function theorem is so one uses the implicit function theorem to get diffeomorphisms P and C. However, since I'm running short of time, I don't have much time to go into this, but what I suggest is you look at the proof in Lee, but don't look at don't study the proof in complete generality. Rather, just take low values of dimensions. I mean, what I did here is good enough. Just take R2 to R2 and rank 1 and see how it works out. That will give you a clear idea how to proceed. So essentially, the inverse function theorem can be used to solve this. So if you still are not clear, maybe we can come back to this later on as well. So I suggest, but you have a look at the proof and yeah.
So we'll take the next question from the one of the live questions. Yeah. So the next question, you can see it there. Shushma Rani has asked, I have a doubt in hypersurface lecture. In the last lecture, you told the proposition that every hypersurface M is locally a graph of a smooth function. You also gave an example of S2 that I also didn't understand. So could you please describe
that?
That?
Okay, fine. So let's so hypersurfaces graphs of functions. First of all, what is a hypersurface? Hypersurface is by definition, if a hypersurface in Rn is a submanifold of dimension n-1. Rn can have submanifolds of various dimensions. When the dimension of the submanifold is precisely one less than the dimension of the ambient space, that submanifold is called a hypersurface. Now, the claim is that this it can be represented as a graph of a smooth function. Well, this should be understood in the proper setting. It's not, for example, let's start with something even simpler than S2. Let's just look at S1. S1 sitting inside R2. This is, from one point of view, it's a closed curve. But according to our definition of a hypersurface, it is indeed a hypersurface in R2. We normally don't use this term hypersurface for a curve, but it fits the definition anyway. We can look at this. So here, the statement is that the key point there in that statement is that it's locally a graph of a smooth function. So, but even for that, one has to be a bit careful. For instance, so let's look at this picture. Now, if I take a point P on S1, say I take a point P which is not, P is not equal to this point or this point. Namely, P is not equal to 1, 0 or minus 1, 0. In that case, I do know that as long as I restrict my attention to, say, P lies in the strict upper hemisphere, the entire upper hemisphere, excluding the endpoints, can be described as, so this is the graph of the function square root of f of x equals square root of 1 minus x squared, and f is a function from open interval from here to here. So this function, I should write it clearer. F of x equals square root of 1 minus x squared, and the domain is minus 1 to n, which is this interval here. This entire upper hemisphere is a graph of this. So the point is, P is indeed contained in a neighborhood which can be written as a graph. Neighborhood in the submanifold which can be written as a graph of a smooth function. Likewise, if P happened to lie in the lower hemisphere as well, somewhere here, strict lower hemisphere, again I get a graph of S. So this time f of x will be negative of square root of 1 minus x squared, and I'm fine. But what happens if P is equal to, say, 1, 0, namely this point here? The problem is that no matter how small a neighborhood of P I take, the submanifold is going to look like this. It's going to go above the x-axis and come below. and more importantly, I get a portion of a curve which cannot be the graph of any function at all, simply because vertical lines, so this is 1 comma 0, vertical lines will intersect the curve 2 times. That violates the criteria for being a graph. So this says it cannot be a graph of a smooth function over the x-axis. However, in this case, notice that if I change my point of view, instead I use the y-axis as a reference, as a domain for my function. See here, I took this -1 to 1, I took it to be part of the x-axis. But if I take -1 to be 1 to be part of the y-axis, so this is -1 and 1, then I'm in good shape, because now I can look at the right hemisphere. And if I look at f of y, g of y equal to square root of 1 minus y squared, again g from -1 to 1 to r, and look at the graph of this over the domain being the y-axis, then this will be part of it. So the statement that locally it's a graph is indeed true, but you just have to be careful graph over which subspace of Euclidean space that you are looking at. Likewise for S2, which is what Sushma Rani has asked about, S2 in R3. Let's draw a picture here. Well, again I have the equator. Anything which is in the strict upper hemisphere, I can look at the function. So this is now the domain, the open unit disk, and I define a function from the open unit disk D2 R. So this is G2. So this is set of all xy in R2 with x squared plus y squared strictly less than 1. On this disk, I define the function f of xy equals square root of 1 minus x squared minus y squared. That gives me the entire upper hemisphere. If I put a negative sign here, I'll get the lower hemisphere. So any point is contained in a neighborhood which can be written as a graph is true as long as I'm in the upper or lower hemisphere. The problem points will be not really problem points, but what I have to change my point of view. If I'm in along the equator, just like I had these two red crosses here, I have to deal with the equator in a different way. So if I'm in the equator, then again the portion of the surface cannot be written as a graph over if the disk is sitting inside the xy plane. But just like we dealt with this here, one can again deal with, but here I have to do 2 more steps actually. So I get the right hemisphere, so this portion is the right hemisphere here. Right. So I can write the entire right hemisphere as a graph over this green disk, the disk enclosed by the green circle, and that will be in the, let's say this is xyz, so that will be in the xz plane. So I'll write y the function as square root of 1 minus x squared minus z squared. So I'll get the right hemisphere. But again, there will be a small issue. There will be one more problematic point remaining, which is this intersection of these two circles will still be there. But that can be, so we have dealt with this thing. What is this? Z, Y, and X. Yeah, ZY plane. You just look at the ZY, put a disk in the ZY plane, this will be inside. So basically, you'll have to look, in the case of S2, you'll have to look at graphs over disks in three different planes: the XY plane, the XZ plane, and YZ plane. Then you can cover the whole submanifold. Can be captured. Hopefully that answers the question. Now, anything else?
Yeah. We have the next question is from Raman Rishi, who is a student, and this question is about the exam. Will the proctored exam be subjective or objective?
The proctored exam will be mostly subjective. It will have a few objective questions.
Can you also tell something more about the type of questions that they can expect?
The type of questions, well, they'll be very similar to the level of difficulty will be more or less the same as the homework problems. And in fact, the type of questions will also be homework, small variants of the stuff that you have been asked in homeworks. Okay, they may not be literally the same as the homework problems, but if you are able to do homework problems, then you will be in a good shape to handle the final exam.
Right, and I think this would be the last question, unless there are more questions in the chat box. So the next question is from Sanam Khan, who is a scientific officer. The question is, does a continuous map carry Cauchy sequences to Cauchy sequences?
Yeah, so this is this is a more basic question than what we have been talking about in this course. But anyway, since I have time, few minutes left, I can address this. So let's look at the answer is no, essentially. So let's look at this function. So the question is, does a continuous function take Cauchy sequences to Cauchy sequences? Answer is no. And a simple example is, for example, let's take f from 0, 1 to r to be f of x equals 1 over x. Then this sequence 1 over n is Cauchy, but f of 1 over n will be n. Definitely not. So that answers the no. We are done now. Okay. Yeah, and we have time now. Is at this point is not. Yeah. Okay. Because it will take at least 10 minutes to answer any question. Yeah. So, all right. So we'll stop here. So we'll stop here, and if you again, I've tried to explain some things, but you should feel free to, even if you didn't understand what I said, but again, you should definitely look at the text by John Lee, and as a general suggestion, I would like to say, if the proofs appear way too complicated, always look at low dimensional thing. So whenever they talk about n-dimensional manifolds or even Euclidean spaces, just put n equals 2 or 3. If you understand and try to go through the proof with that in mind. If you understand the proof with that, then you're in good shape. Okay, so this one you can answer in the
discussion.
discussion session. All right. Thank you.